So this problem relates to homework 2, problem 15. So we are given a boat that can row at 10 kilometers per hour. Part A says how much time is required to row 1.5 kilometers downstream in a river moving 4 kilometers per hour out to the shore. So, how do we figure out the time, the speed, and distance? Well, we know that the change in position is your velocity times time. So we are changing by 1.5 kilometers. And we don't know our time. That's our answer for part A. What is our velocity? Well, we can row at 10. So we know we're going a positive 10, and then we're going downstream in a river moving 4 kilometers per hour. And so we can add 10 plus 4 because our speed is relative to the water surface and that the river moves that water surface as well. And so those two velocities get added. And so you end up doing t equals 1.5 divided by 14. And this gives us 0.107 hours because we are traveling kilometers per hour. And that's part A. For part B, it says how much time is required for the return trip. Well, we're traveling that same 1.5 kilometers, but now we are going upstream. We can row at 10, but now the 4, rather than helping us go faster, it's actually slowing our velocity down. That means we subtract 4 from our velocity. And so our t is 1.5 divided by 6, which we find to be 0.25 hours. So you can see it takes more than twice as long to go back. Part C says, in what direction must the boat be aimed to row straight across the river? Well, the boat moves at a total speed of 10 kilometers per hour. So let's give ourselves a little extra space and let's draw the river. And we'll draw it going this direction and we'll say that the water goes this way at 4, right? So we want to cancel out the motion of the water so that we can just go directly sort of up. That means that our velocity needs to point somewhat in this direction. Now our velocity is 10, so we can take that, and we know we have a y component and an x component, and we can take this triangle. We'll just bring it out, and we'll just draw the triangle somewhere else, where we know this is 10. Well, we know our x, our negative x, that's going to be 4, because we want to cancel out the motion of the stream. And so this is the angle we are asked to find. Well, how do we find that? Well, we can use sine of theta equals opposite over hypotenuse. And so theta equals sine inverse of our opposite 4 over our hypotenuse of 10. And this gives us a theta of 23.6 degrees. And that is the direction the boat must be aimed. So you could say, 23.6 degrees west of north, right? West is to the left of that north up direction. I think you do have to indicate that you are traveling a little bit into the direction of the water. Just given the 23.6 usually is not exactly enough information to describe it. Now we see, suppose the river is 1 kilometer wide. What is the velocity of the boat with respect to Earth? And how much time is required to get to the opposite shore? So let's look at what's going on here. Well, we have our y component of the velocity, an x component. We know this is 4. We never actually figured out what that y component was. So maybe we should figure that out. How do we do that? Well, we could use our angle 23.6, and we could use cosine of 23.6 is going to be adjacent, our y, so say like Vy over 10. And so we get Vy equals 9.16. That is in kilometers per hour, right? And so we can put 9.16 there. Now, this is sort of our rowing speed. In this scenario, when we're still in this picture here, the river gives us 4 in this direction, right? So those two cancel out. Our net velocity ends up being 9.16 kilometers. What was an M there? Yeah, kilometers per hour. And that is our final result. Our final speed relative to Earth. And then it says, look back at the question, suppose the river is 1 kilometer wide. So it's 1 kilometer total. 1 kilometer. So we have to figure out, well, how long is it going to take us to travel 1 kilometer? Well, we know that the change in position is velocity times time, and this is for just constant velocity, no acceleration. And so we're traveling 1 kilometer at 9.16 per hour, and then that's multiplied by time. So t is just 1 over 9.16, and we find the time to be 0.109 hours. And that is how long it would take you to cross back over the river. And so now we look at part E. It says, suppose instead that the boat is aimed straight across the river. How much time is required to get across, and how far downstream is the boat when it reaches the opposite shore? Well, before, up here, we had our initial sort of 9.16. I'm not going to draw it again, but we had our 9.16, we had our 4 to the left, and then the river gave us 4 to the right. And so here, we no longer have that sort of initial split. So we are going just a full 10 across, and the river gives us 4 this way. Well, we can use delta x equals vt again in the same way we did before, right? We're crossing a 1 kilometer river. We're traveling 10 kilometers in that direction, and that's just times time. So our t is just 0.1 hours. Well, how do we figure out how far downstream we went? Well, we can look at our other component, right? We're breaking this problem up into the y direction and the x direction. Here we might want to think about that x as a y since we've drawn that vertically. It doesn't matter too much. We can think about downstream distance. We can call this delta x is our velocity of 4 times our time of 0.1 hours. And so we go 0.4 meters downstream. And so we have answered part A, B, C, and D, and E. And there is all the words. You guys can see all that. All right.